So here we have the formula for period. T equals 2 times pi times the square root of mass divided by spring constant. So 2 times pi represents one full cycle. Clearly it's not going in a circular motion, but I'll show that in a minute, how I can sort of represent it visually. And then obviously we've got mass and spring constant, so only those two affect the period. There's no energy in the equation. You know, as long as those two stay the same, the period will remain the same, and that's what I'm going to show in the demonstration. Also, it's interesting to note that obviously if we change M and K, because they follow a square root relationship, if we were to double the mass or double K, we wouldn't half or double the period. Obviously you get a root relationship, so if you wanted to half or double the period, we would have to quadruple the mass or the spring constant. Here we have a spinning lever, so it's clearly doing circular motion. All I've done is I've got a torch and I'm projecting the shadow onto a wall so you can see the motion. So same as before, but now I'm blocking off one half of the lever, and we can see that even though we know it's rotating, it's very much representing how an oscillator would work, where it accelerates towards the equilibrium and decelerates as it gets far out and then accelerates back in. If we were to plot position against time with oscillation, what you actually get is a sinusoidal wave, which all harmonic oscillation is. This was just a visual representation to show why pi is in the equation, so it's just representing one full cycle, even though the oscillator is just moving up and down. This is just to show the setup, so it's simply a spring and a mass hanging from it. Pull it down and let it go, let it do its thing. So that's how it was filmed. We've got a camera in a fixed position, lighting on it, and we've also got the timer running in real time in the shot, as well as the oscillation the whole time. So it's all one continuous recording. Here it shows the full cycle where energy transforms from one form to another. Starting at the bottom, we pull the mass down, we store maximum potential elastic energy in the spring, so we've got no motion, no kinetic energy, we've just got potential energy, and then we're going to let the mass go. So as the mass accelerates up, that elastic potential energy converts to kinetic energy, so we've lost all this potential elastic energy, it's now all in kinetic energy, and that will carry the mass up into gravity. So now we're at the top, all that kinetic energy has converted into gravitational potential energy in the form of mgh. So we've lost all this kinetic, we've got all gravitational potential, and now it will start to drop back down and convert back. So as we get to this point, all the gravitational potential energy has now converted into kinetic energy, which will then allow it to do work against the spring and storing as elastic potential energy. And like the wheels on the bus, it goes round and around. So off we go. We pull the mass down, start the timer at the same time. So as I said earlier, it's all one take. I will be freeze framing, you know, and changing the speed so we can see the readings, but it was all one continuous take with the timer running in real time. We've got a little bit of swing there, so we'll let it just settle down for a minute or two before we take his first reading, which will be almost like the maximum energy in the system. Obviously over time that energy will dissipate, and therefore we will see the amplitude reduce. But as that happens, we'll see that the period doesn't change. While the amplitude dies down, the period will remain exactly the same. So we'll take his first reading. You can see the start time there. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So we've got 10 oscillations, that's the end time, and for 10 oscillations we get 9.5 seconds. So one oscillation is obviously 0.95 seconds. You just divide that by 10. So we'll let it carry on for a bit now. I'll speed things up a bit. Musical interlude coming up. So we can see the amplitude has died down now. We'll take a second reading about 5 minutes in. See the start time. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. And then we can see the end time. And again, for 10 oscillations, we get 9.5 seconds. So again, I'll speed things up. Another musical interlude coming up. Getting towards the 15-minute mark now, we can see that the amplitude has died down. Take another reading. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. End time, and we can see again 10 oscillations, 9.5 seconds. I'm going to speed things up quite a bit now. Coming up to the 35-minute mark, we've now lost us hundredths of a second, so we'll just have to make an assumption here. So I'll take a reading again at start time. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So we've got 10 seconds there, but we can safely assume it's 9.5. Speeding things up again. did look like nothing was moving there, but it was at 10 times speed, as you can see. It is still moving ever so slightly. So last reading, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's difficult for me to read that one, but I'm sure viewers can see better than me. But there we go, it's pretty much the same.